This call is now being recorded.
Hello. Yes, Ritu. Yes, sir. Sonali. What about Siri?
Yes, sir.
Just can you say more what I thought in the last class yesterday? I discussed about what? Just you can mention key points. Not able to recall. At least my voice is audible, na? Hello?
Yes, sir.
ಅದೇನು ಹೇಳ್ತಾ ಇಲ್ಲಪ್ಪ. Okay, let me share from my side only. Right? I think ನೀನು ಹೇಳ್ತೀಯನ ಪ್ರಣವ್?
Sir, transmission of PAM signal through a band limited signal.
Very good. So we have discussed about the transmission of digital PAM signal through a band limited baseband channel. Then I discussed about the signal design, right? Signal design for band limited channels, right? Two things I discussed. Okay, fine. So let me just recap once again. And let me say what I'm going to say today. Okay, so today we will be discussing about the design of band limited signals for zero intersymbol interference. Okay, so what is the Nyquist criteria for that? Okay. So we are trying to understand what is the Nyquist condition for zero intersymbol interference, and then we will be discussing about the Riser cosine role of filter. So these are the two main topics which we are going to discuss today. So as I was telling, this is the system model what I discussed yesterday, right? So this is my input sequence, input data, right? That will be applied to the transmitting filter. See, first block is the transmitting filter. Okay. First block is a transmitting filter having an impulse response g of t, and second block is what? Channel, right? With an impulse response of c of t, right? So together I said transmitting filter and the channel, together the impulse response will be h of t, right? So that will be what? H of t is equal to convolution of g of t and c of t, right? So then this is the noise will be added in the channel, right? And this is my matched filter, means receiving filter, right? So together of all these three means transmitting filter, channel, and sorry, the receive filter, together I call it as output of that will be x of t. Okay, so x of t is what I have written here is transmitter filter pulse, then channel, then receive filter. Output of these three will be my x of t, right? So I found what is x of t yesterday. What is the expression for that? Even in discrete time also, and right, and at that I will be sampling at t equal to nt, right? And output of that will be going to the detection. Then I will be getting the output data. Fine. So this is what we have discussed yesterday. See, this will be the output of the receiving filter. Okay, what I have written ym or y of m into t, m into capital T, which is equal to, right? So ym is equal to x naught am plus this one summation n is not equal to m an x m minus n plus wm. So it has three parts, right? See, first one is the desired signal. with the desired symbol, what I can say. And this X naught is the gain I said, right? And AM is the sequence of symbols. And second term is due to the successive symbols. Okay, that we call it as an inter-symbol interference. So our aim is to eliminate or correct this inter-symbol interference. Anyhow, the third term is due to the additive weight Gaussian noise. Okay, so I hope you could get back to this equation. This is very, very important equation. Okay, this is output of the receiving filter, what I was telling. So as I said, our goal is to minimize this inter-symbol interference. To do that, there are two different ways. One, I can use a filter, right, which is band limited. Right. The second thing is the equalizer. Okay, so we will be discussing about those two things I said in this module. Right. And I discussed about this I pattern. Right. So what this I pattern will say as, so it will indicate means the amount of noise and as well as the inter-symbol interference can be viewed on the oscilloscope I said. Right. For PM signals, any signal what you do, that I pattern will be displayed by applying the received signal to the vertical input and with the horizontal sweep rate, which is set at a symbol address 1 by T. Right? So whatever the display we get on the oscilloscope, that we call it as an I pattern. So I told about this what is I pattern is having, right? And this is the optimum sampling time, or we can say best sampling time, right? And this is from year to year. I said it is sensitivity to timing errors, and from year to year it is noise margin, and here is what I said, it is the distortion of zero crossings, right? And this will be the what peak distortion. Okay, so the effect of ISI means the effect of inter-symbol interference is to cause the eye to close. So this is eye opening, what we say, right? So because of this ISI means inter-symbol interference, the eye will close. That means if this is very small, then I can say inter-symbol interference is more. Right. So the inter-symbol interference distorts the position of the zero crossings, and that causes, if this zero crossing position distorts, then that causes reduction in the eye opening, right? This I said this is eye opening, right? So it causes the system to be more sensitive to synchronization errors. So this is all what I have discussed. Then let me start for today's this one, that is a design of band limited signals for zero inter-symbol interference. So that what is the Nyquist criteria. As I said, I am assuming that means the band limited channel, and it has ideal frequency response. Okay, that is C of f will be equal to 1 when f is less than or equal to w. So whatever I discussed in the first class of this module, that frequency response C of f, the same thing, right? Means it is a rectangular pulse which is constant and having a value of magnitude of 1 from minus w to w. That is what this one. Okay, so we are interested here about the pulse x of t. Okay, that has the spectral characteristics x of f is equal to this. So x of f is the what Fourier transform of x of t. So I write here x of t is equal to what? This is the expression for x of t, right? That is over the interval from minus w to w, x of f into e power j2 by ft into df, right? So we are interested in determining the spectral properties of this pulse, okay? That results in no inter-symbol interference, okay? Means if the pulse shape is what should be the pulse shape and what are its properties. So if it is like that, then do you think that it will not result in inter-symbol interference, right? So we will be discussing about that. As I said, the channel, right, which is band limited, right, and the Fourier transform of the signal at the output of the receiving filter, that is x of t, etc., right? So in frequency domain, I have written here expression. I think in the first slide itself, I have shown this. What is this? Here, x of t is equal to transmit pulse, channel, and receive filter, right? So that this is in time domain I have written. So I have written here in the frequency domain this expression. See x of f, which is equal to frequency response of the transmitting filter, frequency response of the channel, and frequency response of the receiving filter. So x of f is equal to gt of f into c of f into gr of f. And I know what is c of f, right? I have already defined what is c of f. So c of f is equal to, I said, c naught into e power minus j 2 pi of t naught. Just I'm substituting the value of c of f here. And since this time delay, okay, t naught, we are setting it to 0. So then e power 0 is 1. And I'm making it c naught is equal to 1. So with that, I can write x of f is equal to gt of f into gr of f. That's what is written here, right? I said gt of f and gr of f are the what? Transmitter and receiver filter frequency response. And I said c of f is what? Frequency response of the channel. So any questions to be asked, we can ask. Is it clear, this equation, what I said? Yes, you should respond. Hello?
Yes, sir.
So this equation is clear. Just I have written output of the receive filter in the frequency domain. Okay, I said x of f is equal to gt of f, c of f, and gr of f. I said gt, and I substitute the value of c of f, and I'm letting t naught equal to 0. Means t naught is the delay. I'm letting delay is not there. So t naught equal to 0. If I make t naught equal to 0, this becomes 1. And I'm letting the magnitude, the c naught, is also equal to 1 for convenience. So with that, I can say x of f is equal to gt of f into gr of f. So what is this gt of f and gr of f? These are the frequency response of the transmitting and receiving filters. And okay, this already I defined, right? I said what is c of f, and this is what the expression what I written yesterday as the output of the receiving filter, which is sampled at t equal to mt, right? And then this is the modified version of this, right? So ym is equal to, I said, x naught em plus this second term plus third, and I discussed about this also. I said first term is the desired one, second one is due to ISI, third one is due to additive noise, right? Our goal is to eliminate the second term. Okay. So to remove the effect of intersymbol interference, I say it is necessary and sufficient that x of mt minus nt, okay, which is equal to 0 for n is not equal to m, and x of 0, okay, is not equal to 0, you can say. So when n is not equal to m, means the sampling, right, x of mt minus nt, right, that should be equal to 0. And x of 0 should not be equal to 0 for other values, right? So we can assume x of 0 is equal to 1 without losing any generality. So in a simple way, this implies that the overall communication system has to be designed such that this what x of nt is equal to 1 when n equal to 0. Okay, so when n equal to 0, means x of 0 should be equal to 1, right? And for other values of n, when n is not equal to 0, this x of nt should be equal to 0. I hope, what do you understand by this? I said x of t is the pulse at the receiver side, right? Means output of the receiving filter. Means this is the, we are interested in pulse, I said, right? So I said that the value of x of t or x of nt should be equal to 1 means what? I should get a peak pulse at only, means n you can think that it is time axis. Okay, only when at n equal to 0 I should get a maximum amplitude of the pulse with a magnitude of 1, and for other values of n it should be 0. Right? So this condition is known as the Nyquist pulse shaping criteria, or we say Nyquist condition for zero intersymbol interference. I don't know how many of you are listening this and hearing this and understanding this. Is it understood from your side? I said to remove the effect of intersymbol interference, right? It is the necessary and sufficient that x of mt minus nt, okay, which should be equal to 0 for n is not equal to m. Okay, and when n is equal to m means I get x of 0, right? So x of 0 should not be equal to 0, means it should be equal to 1, I am assuming. Okay, I can assume x of 0 is equal to 1. So I said this is the expression, and I call this equation as the Nyquist pulse shaping criteria or Nyquist condition for zero intersymbol interference. I hope, is it clear? Will you be able to visualize what should be the shape of the pulse? Which pulse can have this type of property? Means at only n equal to 0, it should have an amplitude of 1 peak, and for any other values of n, its magnitude should be equal to 0.
Unit impulse.
Yeah. So in other way, what I can say, this is the means to say the Nyquist condition for zero intersymbol interference. I said no, this is the necessary and sufficient condition. Okay, that pulse x of t should satisfy. What is that? X of nt is equal to 1 when n equal to 0, and it is 0 when n is not equal to 0, right? And to express in frequency domain, right? X of t is a pulse in time domain. So capital X of f is its Fourier transform, right? So that must satisfy this equation, means summation. This is in discrete what I have written. Summation m is equal to minus n to infinity x of f plus m by t, which is equal to capital T. Okay. So I think equation 20 and 21 should be remembered and understood very well, because this is the Nyquist condition to have zero intersymbol interference. I think we are not discussing about the proof of this because it is out of the scope of your syllabus. Okay, only they will ask for 2 marks or 4 marks. They will ask you so many times. They have asked, this is an important topic. Okay, what I wanted to say, they will ask you to write the Nyquist condition for zero intersymbol interference. So you should write these 2 equations. Okay. Fine. I will take up things. So this is what I expected from you to imagine pulse, right? See what it is happening at this is the n is equal to, you can think, right? This x-axis is n. So when n equal to 0, it is having a maximum amplitude. So I am assuming this is 1. But as n increases, right? Means that n is not equal to 0. This at this point it is 0. It is vanishing, right? At n equal to only t, from minus t to t, it is having this one. At n equal to 0 only, it is having maximum amplitude. For other values of t, it is 0. Means we call this as zero crossings. These points at t equal means at t, 2t, 3t, 4t. Similarly, negative side also means plus or minus t, plus or minus 2t, plus or minus 3t, plus or minus 4t. So these points we are calling it as zero crossing points. So at this point, its magnitude is 0. Okay, the x of t value will be 0. Means if I have this type of pulse, right, I will be able to have zero intersymbol interference. Means if I transmit this type of signal over the band limited channel, right, I will be able to have a signal at the output of the receiver which will not be having zero intersymbol interference. Okay, but there are some difficulties to have this type of signal. Okay, I will come to that. Whether is it physically realizable or not, and other challenges are there. Okay. I hope this is clear. This equation. This equation is very, very important. What I said, that x of n is equal to 1 when n equal to 0, and 0 when n is not equal to 0. In frequency domain, we write this. Right? That is from m is equal to from minus n to infinity, x of f plus m by t should be equal to t. Okay. So let me go to the next. So I am considering here 3 cases. Okay, 3 cases. What are those 3 cases? Means if the channel has a bandwidth of W, right? Then I said that the frequency response will be what? C of f equal to 0 when the frequency is greater than W, right? And even the value of x of f is also equal to 0, right? For f greater than W. Right? So I was talking about that t, symbol duration, right? Right. So when a t is less than 1 by 2W, or I can say 1 by t is greater than 2W. So t is the interval, okay, and 1 by t is the bit rate. What I can say, bit rate or symbol rate, right, is greater than 2W. 2W is what I said, bandwidth of the channel also, and this is the bandwidth of the signal also. You can think. Okay, so let us assume that this is my x of f, okay, and this is my c of f also. X of f and c of f both are same, what you can think. Okay, so when this 1 by t, see at this point it is there, right? If that is greater than 2W, see from here to here it is W, right? So 2W means this is the bandwidth of this pulse, right? Right. So when it is greater than 2W, then there will be no overlap, isn't it? There will be no overlap between the subsequent pulses or successive pulses. I hope you are understanding. I am replicating this. This is my x of f, what I can think. X of f, which is equal to c of f also. Okay. What is x of f? It is Fourier transform of the signal. Means output of the receiving filter also. I can think. 3 things you can understand. Another one is the frequency response of the channel is also like this, right? And its bandwidth will be 2W. So what I'm thinking here, when t is less than 1 by 2W or 1 by t is greater than 2W, means it repeats every 1 by t, right? If it is greater than 2W, right? So what I have written here, I'm denoting this sum of all these pulses as z of f, right? So it has no non-overlapping replicas of x of f. I said that this one pulse is x of f, right? That repeats every 1 by t, right? And what I said, that will be greater than 2W. So then since there will be no overlap, okay, that ensures that to ensure the value of this z of f means what I wrote, that is a condition, right? X of f plus m by t. Okay. See here, take a notation slightly different, which is equal to, should be equal to t, right? To ensure. So in this case, there is no way that we can design the system with no intersymbol interference. Okay. The next case is same thing I repeated here. When t is less than 1 by 2W, so there is no choice for x of f to achieve this z of f is equal to t. Okay. And there is no way to design the system with no intersymbol interference. Okay. The next case is when t is equal to 1 by 2W. Okay. Or 1 by t is equal to 2W. So 2W means what? So this is the bandwidth of the x of f, right? That is 2W. Right? So here what is happening? It is exactly joining. It's attaching. So this is W. W is equal to 1 by t. Right? So this is what the pulse means. It repeats when x of f repeats. Exactly, it is aligning with the edges of this one, right? So it is clear that there exists only one x of f that results in z of f is equal to t. Okay, that is when T is equal to 1 by 2W. I hope you are understanding this waveform. So I said 1 by T is equal to 2W. That is the Nyquist rate, what I can say. So replicas of x of f means I said this is my x of f. Okay, this is x of f that repeats replica, right? Separated by 1 by T, right? Are about to overlap. Just it is edging, right? So this will ensure that there exists one x of f that results in this z of f equal to T.
Yes.
So same thing, one more diagram I have shown with the same thing. So what I said, T, when T is equal to 1 by 2W, right, or 1 by T is equal to 2W, I said the Nyquist rate, the replications of x of f separated by 1 by T are shown here, right? So I said in this case, there exists only one x of f that results in z of f is equal to T. So I said one x of f results, right? That one x of f can be written as this one, x of f is equal to T when f is less than W. Okay, for other values, it is 0. This is in frequency domain, what I wrote in x of f is equal to. Right? If I want to write this in time domain, I can write that as sinc function. So x of t is equal to sinc of t by t, small t by capital T. Okay, that is why I said only one pulse exists. Right? There exists only one x of f that results in z of f is equal to t. Okay, you are aware of the sinc function, no? What I have shown at the beginning. To what I said, that to have zero intersymbol interference, the pulse shape should be like this. Yeah, this is what we write as a sinc of small t by capital T. Okay, is it clear? This pulse.
Yes, sir.
First case is when t is less than 1 by 2W, there is no way to design a system which is having no ISI. Second case, I said with t equal to 1 by 2W, I said there exists one pulse that results in z of f equal to t. Okay. Yeah. So in frequency domain, I wrote that x of f equal to t when f is less than W. Otherwise, it will be 0. But in time domain, I can write that as a sinc function. X of t is equal to sinc of small t by capital T. Right? So this is what I repeated once again, that pulse I have shown the here only now. Yeah, sinc pulse, right? This is a T. Okay. Just to recap. That is one pulse. Because this is another pulse, right? This is another pulse. Means if I have a signal like this, then I will not be having ISI. Because why I will not be having ISI? See, this is what one peak, right? And the rest are zero crossings. Next, for other pulse, it is at one peak, right? Other things are at zero crossings. Fine, this is a first, second symbol, and this is a third symbol. At this point only, it is maximum. For rest of the things, it is zero crossings, right? And next one, at this point, it is having peak value, right? If I have a signal like this, then I will not be having the zero. I will not be having intersymbol interference. So this is what I said, no intersymbol interference in these cases. I hope you are able to visualize this. Yes,
Yes, sir.
yeah, this is what the sinc function first pulse. Then I gave a second pulse, then the third pulse, then fourth pulse, right? Then I'm saying no ISI, and here I'm marking this as zero crossing points, right? Where this pulse magnitude is 0. Okay, but for other pulse, it is maximum at that point. And for rest of the intervals, it is 0. Right? Okay. Okay. Yeah. Right. Already I told about this, right? Just now. Right. The sinc function with adjacent to this one, no zero crossings. At zero crossing, its magnitude is 0. I said this is what the pulse which I get 0 into symbol interference. In time domain, I'm denoting the sinc T divided by capital T. Can be written as what? Sin pi t by t by pi t. Means sin pi x by pi x, right? This is what the sinc function. So, the smallest value of t for which the transmission with 0 into symbol interference is possible is what? T equal to 1 by 2w. Just what I've shown, I'm filling in words here. So what we understood is what is the smallest value of t for which transmission with 0 ASI is possible is t is equal to 1 by 2w. Right? And for that value, x of t has to be a sinc function. Right? So what is I said already, what is the difficulty with that function? So the difficulty with this choice of x of t is that it is non-causal and non-realizable. I hope you are aware what is causal system and what is non-causal. Anyone can say what is causal and what is non-causal? Yes, you have studied very much in signals and systems. Causal and non-causal. I'm saying this pulse is a non-causal and non-realizable. What do you mean by causal?
So which do not depend upon past outputs.
Yeah. Okay. So I'm saying the sinc function is a non-causal and it is not physically realizable, right? That is one difficulty. The second difficulty with this pulse is, pulse shape is, its rate of convergence to 0 is also slow. Right? Means it is decreasing. No? At what rate it is decreasing? So it decreases at a rate of 1 by t, you say. Okay, the rate of convergence to 0 is also slow. So the tails of x of t decays as 1 by t. So consequently, small mistiming error even in the sampling, the output of the matched filter and the demodulator results in an infinite series of ISI components. Okay, so such a series is not absolutely summable because of the 1 by t rate of the decay of the pulse, and hence the sum of the resulting leads to, means ISI will not converge. So just to say, this is what the example sequence is given: 1 plus 1 by 2 plus 1 by 3 plus and so on. It won't converge. Okay, I hope this you are familiar, na? This sequence. Are you familiar with the sequence? Have you tried any time? Do you think that this will converge the sequence? No, right? So just given one example of that. So as I said, these are the two difficulties with this pulse shape, right? One is it is non-causal and non-realizable, and second thing is that pulse shape, right? The rate of convergence to 0 is slow because it decays at what rate? 1 by t. So decaying at that rate will not converge. Yeah, this is the third case, that is when t is greater than 1 by 2w. Okay, again here this should be z of f, so taken from different source. That is why notations are different. Just try to understand that. Okay. So that consists of overlapping replications of x of f separated by 1 by t. Okay, so here there is an overlap of that, right, separated by 1 by t. So in this case, there exists numerous choices for x of f such that z of f will be equal to t. Okay, so this is the case with which we will be able to obtain numerous choices of the x of f that will satisfy z of f is equal to t. Okay. What the case I have shown here. That is when t is greater than 2w. Right? So there exist numerous choices for this pulse shape, so that z of f equal to t. Right? So in this case, a particular pulse spectrum that has been widely used is this one. What is that? Raised cosine spectrum. riser cosine spectrum. Means the pulse shape which is having this type of behavior is we call it as a riser cosine spectrum. So we'll see what is its frequency characteristics and advantages of that pulse. So we define mathematically like this. That cosine role of a riser cosine filter. Okay. So a particular pulse spectrum for T greater than 1 by 2 WKs, right? So that has the desirable spectral properties and has been widely used in the practice. So that is known as the riser cosine spectrum. So in time domain, we define that riser cosine spectrum like this: x of t is equal to, this is a sinc function. First part is right. Sine of pi t by t divided by pi t by t is nothing but sinc of small t by capital T, and this is cos of pi alpha t by t divided by 1 minus. With this, we can write it as 4 alpha square t square by t square, or like this as a 2 alpha t by capital T whole square also. And here I am saying alpha is the role of factor, and its value of alpha lies between 0 to 1. So I will come back to this. This is slightly big equation which you need to try to understand what is this, right? So this is in time domain and this is in frequency domain. In frequency domain, the riser cosine spectrum will be written as XRC of f is equal to T, capital T, when the value of f is less than or equal to this 1 minus alpha divided by 2t. And between this range, when frequency lies between 1 plus alpha by 2t and greater than 1 minus alpha by 2t, during that time, this is the function 1 by 2 of 1 plus cos of alpha pi capital T by alpha of f minus 1 minus alpha by 2t. And it will be 0 when f is greater than 1 plus alpha by 2t. I will show you the spectrum of that. Okay, same thing I did here. So I will come back to this after showing this diagram. Yeah. This is what I wanted to say. Pulse having a riser cosine spectrum. Here you treat this beta as alpha 1, whatever I've written in that equation. Okay. See, for different values of alpha, as taken, that is one is 0, 0.5 and 1. So 3 cases we have shown here. So this is when the square pulse, exact square pulse is when alpha is 0, and this is for alpha is 0.5 and this is for alpha is 1. So alpha is 0.5 and alpha is 1, it is slightly exceeding this one, right? When alpha is 0, means in this case it is beta, is 0, we get a perfect square pulse. Okay, this is in frequency domain, that waveform, and this is in the time domain. So what I wanted to say here is, the bandwidth occupied by the signal beyond the Nyquist frequency 1 by 2, we call that as excess bandwidth. Okay, and it is expressed as percentage of the Nyquist frequency. So in the diagram, what I've shown, beta is nothing but alpha, as far as my display is. Okay, so alpha is equal to 0.5, we say excess bandwidth, which is equal to 50%. We say when alpha is 1, the excess bandwidth is 100%. Okay? And this is the equation, same what I've repeated previous slide. So here I wanted to say, when alpha is 0.5, I say 50% excess of bandwidth is there. Okay, it occupies an excess of bandwidth of 50%. When alpha is 1, so exactly it is 1 by t, right? So its bandwidth varies from minus 1 by t to plus 1 by t. Means 100% it is excess of bandwidth. When alpha is equal to 0, it is exact square pulse. Okay. So this is what the shape of the riser cosine pulse. I think with my notation alpha, it is there here. Okay. So shown with alpha equal to 0 case, alpha, this is alpha is equal to 0.5 case, and this is an alpha is 1 case. Okay. So alpha is 0 is ideal, like a square wave. Alpha is 0.5, I said there is excess of bandwidth of how much? 50%. And when alpha is 1, so it's excess of bandwidth of how much? It is 100%. Okay, this is in time domain, and this is in the frequency domain. Okay, sorry, this is in time domain, this is in the frequency domain, right? So exactly a sinc pulse, right? We wanted this to be 0. So I am able to minimize, means when alpha is 0, the side lobes, right? Magnitude is maximum, but it is exactly coinciding with this is 0 and this is capital T, right? At capital T it is 0 and keeps vanishing. So as the value of alpha increases, right? When alpha is 0.5, its magnitude is less. And when alpha is 1, it is very, very less, right? I hope you will be able to understand this difference in magnitude between T to 2T. What is its magnitude? So this only leads to intersymbol interference, right? If this magnitude at from T to 2T is more, then it leads to intersymbol interference. It has to be tried to minimum. So that is happening when alpha is equal to 1. Pakka, right?
Yes, sir.
So this is the raised cosine pulse. Okay, this is in time domain and this is in the frequency domain. What I want to say. Yeah. So let us discuss about that waveform. So I said, so in the first case, I said when it is a single pulse, single sinc function, I said it decays at what rate? 1 by t. And here, for this tail, the tail of that x of t decays as 1 by t3. Okay, for, we can think this as alpha. Okay, when alpha is greater than 0. Okay, so I have shown for three values 0, 0.5, and 1. So the tail of that pulse decays as 1 by t cube. So a mistiming error in sampling leads to a series of ISI components that converges to a finite value here. In the previous case, it was not used to converge, right? Yeah. So based on the smooth characteristics of this raised cosine spectrum, so it is possible to design practical filters for the transmitter and as well as the receiver that approximate the overall desired frequency response. What is the overall desired frequency response? Already I told about x of f is equal to gt of f into gr of f. So that is what is written here. So in the special case where the channel is ideal, in that case the value of c of f is equal to 1 means the frequency response of the channel is equal to 1, right? When f is less than w. So in that case, x RC of f is the what? Is the frequency response of the raised cosine roll-off filter. That should be equal to the frequency response of the transmitter filter and the frequency response of the receive filter. This is what I was discussing at the beginning, right? Started with x of f is equal to gt of f, c of f, and gr of f, right? Isn't it? So gt of f and gr of f are the what? Frequency response of the transmitting and the receiving filters. So if the receive filter is matched to the transmitter filter, so gr of f is equal to gt of f, then we can write x rc of f is equal to what? We can substitute gr of f also is the gt of f, so I can write gt of f whole square. Okay. So in gt of f is equal to what? Square root of this, right? This is understandable, and we say gr of f is equal to complex conjugate of gt of f. And here I have taken T naught is the nominal time delay that is required to ensure the physical realizability of the filter. So I have written GT of f means this is the frequency response of the transmitting filter, right? Is equal to square root of XRC of f means raised cosine roll-off filter frequency response into e power minus j 2 pi of T naught. So here what is this T naught? T naught is the delay. Okay, that is required to ensure the physical realizability of the filter. Right. So to conclude about this, the overall raised cosine spectral characteristics is split evenly between the transmitting filter and the receiving filter. What you can say. So the additional delay, what I'm saying, T naught, right, is necessary to ensure the physical realizability of the receiving filter. So this is all about raised cosine roll-off filter. I think this is important for the examination point of view. Okay, so though you do not have the proof, okay, of doing that Nyquist criteria to have zero intersymbol interference, but so what is the best pulse shape, okay, and what is that about raised cosine roll-off filter? They will ask. So this is what my today's this one. If you have any questions to be asked, we can ask. Okay. So So I discussed about two things. One is what is the Nyquist criteria to have zero inter-symbol interference, right? I said x of nt, which is equal to what? 1 when n equal to 0, and it is 0 when n is not equal to 0. So in frequency domain, we write summation m is equal to minus infinity to infinity x of f plus m by capital T, which is should be equal to t, right? So to have that, taken three cases. When t is less than 1 by 2w, what happens? When t is greater than 1 by 2w, what happens? And when t is equal to 1 by 2w, what happens, right? So those three cases, then after considering those three cases, I came to this raised cosine roll of filter. Okay. So if you have any questions to be asked, you can ask. This is what I discussed it from today from here, right? Yeah. The x of f is the output of the receiving filter IC. Yes, anything to ask, you can ask. Okay. So this slide is very, very important. What you're supposed to understand. X of nt is equal to 1, n equal to 0, and it is 0 when n is not equal to 0. So this is the necessary and sufficient condition for x of t to satisfy zero inter-symbol interference. Yes, any questions you have? Yes, now it is question and answer session. What you all can say. I think nobody has charted. You just enter your USN in the chat box. Okay. So today 36 people are there out of. Yes, any questions if you have, you can ask me. Yes, Shreyas.
Yes, sir.
You understood, man, all the three things. What is the Nyquist criteria to have zero inter-symbol interference? Then what is the difficulty? I said the three cases I considered, right?
Yes,
T
sir.
greater than 1 by 2w, how the x of f repeats, right? When t is 1 by 2w, what we get? When t is greater than 1 by 2w, what we get, right? And then we go for raised cosine roll of filter. And what is its time domain expression, frequency domain characteristics, and its characteristics also we have studied, right? We have discussed it. Yes, is it clear? You just, I think first time may be difficult to understand. So with all these efforts I made, I tried to convey as simple as possible with all the such diagrams. I will share the slides you can have, and if you have any difficulties, you can always discuss. Okay. Gautam. Gautam is not there. Gautam is there.
Yes, sir.
Understood, man, about the Nyquist criteria for zero ASI and as well as the raised cosine roll of filter.
Yes, sir.
Okay. So you don't have any questions?
So once I'll study and then I'll ask the question.
Fine. Yeah, it takes time. This module is slightly hard compared to other modules. So we need to put some more efforts. I will share all the slides because we discuss in time domain as well as frequency domain and in discrete mode also. Okay, so the moment I say the summation of something, that will be I am representing in the discrete domain. Okay. If I say integral, then it is in continuous. So you need to switch over the visualization of those pulses from continuous time to discrete time. but it is a very interesting and important topic also for understanding the design of any digital communication system. Okay, about transmitting filter, receiving filter, and channel. So we are talking about the pulse shape. Yes, then if you don't have any questions, then we can question, or if you can't ask, you can chat also. I will answer. I tried to contact Siri, could not speak. Then Sonali also could not speak. He left her what already. Yes, Sudarshan. Sudarshan.
Yes, sir.
Aman Sharma, I think he left.
Yes, sir.
Yes, Sonali. Sonali is not talking only. Yes, then you don't have any questions to ask? I think today Vishnu has not come.